This is problem 41 from chapter 12. In this problem, the elevator starts from rest. At the first floor of the building, it can accelerate at 5 feet per second squared and then decelerate at 2 feet per second squared. So if speeding up is positive acceleration, slowing down is going to be negative acceleration. Determine the shortest time it takes to reach a floor 40 feet above the ground. So we're going from here up 40 feet. The elevator starts from rest and then stops. So for our velocity versus time graph, we have to start at 0 and end at 0. We need to draw the acceleration versus time, the velocity versus time, and the position versus time graphs. The first thing that we need to determine is how we want the acceleration versus time graph to look if our only concern is getting up to this floor 40 feet away from where we started as fast as possible. So if you want to do this as fast as possible, and you also have to be at rest when you reach the floor 40 feet above the ground, you want to speed up using this acceleration of 5 feet per second squared. Oops, I put meters in here. Okay, so we're going to speed up at 5 feet per second squared, and then we're going to switch right away to slowing down. So we're never going to travel at a constant velocity if our goal is to get there as fast as possible. So then we're at -2, and then at some time we reach 40 feet above the ground and we should be at rest then. The area underneath the acceleration versus time graph is the change in velocity. And if we're starting at 0 and ending at 0, then this area here has to be the same as this area here, so that the total area underneath the acceleration versus time graph is 0. For our velocity graph, the acceleration here is constant and positive, so the slope of our velocity versus time graph is positive, and then here we should be at 0 again. And then for our position versus time graph, the slope starts at 0 since the velocity is initially equal to 0. This is the maximum velocity, so we speed up. And the slope becomes more and more positive, and then the slope has to end here at 0. So that's something like that for position versus time. Let's call this time here T2, and this time is T3, so I have T2 and T3, T2, and T3. I want to find the shortest time to go 40 feet. So when I reach 40 feet here, this is 40 feet, I want to know what that time is. We already drew the graphs. I don't need to add anything to the graphs. If I want to say the slope here is 5 feet per second squared, the slope here is -2 feet per second squared, I could do that. We have our maximum velocity here, and the area underneath the velocity versus time graph is equal to what? That is the change in position. I want the total change in position as I go from here to here to be 40 feet. So I can say 40, let's leave the units out. So the total area under the graph here is 40. Let's just put that in here so we know where it's coming from. That should be equal to the area of this right triangle plus the area of this right triangle. Both of those right triangles have the same height, although I don't know what that velocity is. But I could figure that out. One way to do this is to go back to the acceleration versus time graph, and we said the area underneath the acceleration versus time graph was the change in velocity. So if you just look at the area underneath the graph as we go from 0 to 2t, that's going to be the velocity that we're at here since we started at 0. So that area is equal to 5 feet per second squared times t2. And so that's what the velocity is when we're here. So the area that I have here is equal to this area, that's a triangle, so that's 1/2, times the base, which is t2, times the height, which is this velocity, which is 5 times t2, plus the area of the second right triangle here, and the height of this right triangle has to be the same as the height of the first right triangle, and so that's 1/2 times the distance from here to here, that's t3 minus t2, but let's just call that delta t23. So times delta t23 for the base, and the height is 5 times t2. So that's one equation, but it has two unknowns. Those unknowns you could either say are t2 and t3, or t2 and delta t23. So I'm going to need another equation. We found the height, or the velocity that we have here, looking at the area underneath the first part of the acceleration versus time graph, but we said that that velocity has to be the same as what we used over here for the height, which is also the area that we have for this piece here. So we said if we speed up and get to this velocity, because we're ending at 0, the total area underneath the graph has to be equal to 0. So from that, we have 5 times t2 is equal to, this area would be delta t23 times, you could either say 2 or -2. So the area is underneath the curve, and so it'd be negative area, but this positive area would have to be equal to this positive area. So you could either write it like this, delta t23 times 2, or if you wanted to say the total area underneath the curve is equal to 0, it would be 5, 2, and then you would say that this is negative area, so it would be a -2, so this would be equal to 0. Okay, so either way, and this is from the acceleration versus time graph, looking at the area. Okay, so now I have two equations. There's one equation, there's the other equation, and I'm going to take equation 2 and solve it for delta t23. So I have delta t23 is equal to 5/2 times t2. And then I'm going to put that into equation 1, so I just have one unknown. So that's 40 is equal to 1/2 times, actually let's call that 5 divided by 2, and then I have a t2 squared plus 1/2 times this delta t23 is 5/2 t2 times 5 times t2. So I have 40 is equal to 5/2 times t2 squared plus 5 times 5 divided by 2 times 2. That's 25 divided by 4 times t2 squared. I'm going to let you finish solving that on your own. So you're looking for t2. You can pause the video if you need to. And you should get t2 is equal to 2.138 seconds. But that's not actually our final answer, because we're looking for t3 because we want the time to go 40 feet. So then we have to go back to our equation here. So we have delta t23 is equal to 5/2 times t2. So that's 5/2 times 2.138 seconds. And then after I have that, I can say t3 is equal to t2 plus delta t23, since delta t23 is just equal to t3, minus t2, and so I have 2.138 seconds plus 5/2 of 2.138 seconds, and that gives me t3 is equal to 7.483 seconds, and that is my final answer. Once again, if they're asking you in a problem to draw the graphs, all I'm looking for is a sketch of the graphs, and I don't need you to include any numbers or equations unless either the problem in the book specifically asks you to do that, or I specifically ask you to do that when I assign the homework. And that concludes problem 41.